In this video, I will measure an amplifier's amplitude and phase linearity. For the setup, I've connected a 10 dB amplifier to the output of a signal generator and the input of a spectrum analyzer. I have my signal generator set to 1 GHz CW at negative 10 dBm stimulus, and on the spectrum analyzer, I've configured a time domain power zero span trace, and I'm measuring 1.24 dBm output power from the amplifier. Okay, so let's go ahead and start with the amplitude sweep of the stimulus. So we'll go into the RF block on the signal generator. And we want to run this in fixed attenuation mode. And so we have the attenuator set to fixed right now. And then we'll go down to RF level sweep. And we'll set that level sweep to sweep between negative 30 dBm and positive 10 dBm, 40 dB range, in 1 dB step size. We'll dwell for 10 milliseconds at each sweep point. Let me turn that on. Now we can see that signal is ramping. We can see at the top of this power range, the amplifier is compressing a little bit. I could stabilize this trace by adding a video trigger, or if I had some other way of synchronizing the sweep, I could do so. This works pretty well. We can measure the output amplitude of the amplifier. We don't have any phase information here, but we are limited in the minimum sweep time. So if we look at this dwell time here, the fastest we can dwell is 1 millisecond. So let's go ahead and minimize that. Let's reduce our sweep time. And we can see this curve is relatively smooth. We no longer see that stair step. And just to make sure that's not from the video bandwidth, let's try increasing that. Okay, sure enough, that's from insufficient resolution bandwidth. So this is pretty fast, but in a production setting, maybe we don't even have that 1 millisecond per point times each of the different power levels to wait. Maybe we want to do this on the order of microseconds per power level. So there must be a better way. So let's turn off the RF level sweep. And we can do the exact same thing we just did in the RF section. We can actually do that in the baseband. We can do that much faster. So we go to baseband, power sweep. We have a stair-step stimulus over a 40 dB range, the maximum signal level at plus 10 dBm, the minimum signal level at negative 30 dBm in 1 dB steps. And let's go ahead and turn that on. We can see the same stimulus as before. Now I have access to the baseband trigger, and then I can arbitrarily reduce that sweep time down to 20 milliseconds, down to 10 milliseconds, down to 5 milliseconds. And as long as I have sufficient resolution bandwidth to capture the effectively amplitude modulated signal, I should have an accurate time domain power. We don't even need to stop there at having these discrete power steps. We could actually use a linear ramp, and then we have continuous data from the minimum power to the maximum power that this amplifier is designed to be operated at. So let's change the shape of this power sweep from stair step to linear ramp, operating over 40 dB from negative 30 dBm to positive 10 dBm at the top. For now, let's just go ahead and set this up with a 5 millisecond sweep time. We can let the fall time be 1 millisecond and the RF blanking time be 1 millisecond. And we can reduce our sweep time on the spectrum analyzer to, say, 10 milliseconds. Or we could even reduce that down because we only care about probably the first 5 milliseconds or so. And there we have the amplitude sweep. We just need to make sure we have sufficient resolution bandwidth as before. Whenever you have a fast sweep, that should be sufficient there. And if we have too high of a resolution bandwidth, we'll notice we have maybe a little bit more noise on the trace, just since we're allowing too much noise to degrade the measurement on the low end of the signal. But that's really the only penalty we pay. So how do we get phase information from this if we wanted to measure an amplifier's phase linearity? Well, for that, we can't just do a simple amplifier spectrum measurement. We actually have to use a signal analyzer that's going to give us both the magnitude and the phase. So the simplest way is to open up an IQ Analyzer measurement channel. And we can increase that measurement time as we did before to 5 milliseconds. I'm going to reduce the sample rate down to the equivalent of the resolution bandwidth that we had before. Maybe 1 megahertz was sufficient. Let's trigger the signal so that it starts capturing at the beginning of this power ramp. We see we have basically the same trace as before. But in IQ Analyzer mode, not only do we get the magnitude, but we also get the phase. So let's go ahead and add an IQ vector, and we can look at the real and imaginary components versus time, and we can even get a spectrum. We get all that information from IQ analysis. So as we'd expect, the spectrum is just a CW line and swept in power. But the thing that's most interesting here is the IQ vector. We can see that it's initially a straight line from the origin, but then at higher signal levels, the amplitude increases and then decreases. So this is in the overdrive region. And through this entire compression to overdrive region, the amplitude's phase is changing. So for every single point here, we could use the arctangent of the Q over I, and that would give us the phase at each point, and then perform a linear fit along some of the linear region points, and that would give us the phase deviation from the linear operation point of this amplifier. And that would be a good first order pass on amplitude and phase linearity for an amplifier. However, there's a challenge when you have a frequency reference that is not shared between the input and the output. Let's say this is an over-the-air signal and you don't have the benefit of a 10 megahertz reference that's connected between your generator and the analyzer. What ends up happening is a phase rotation as the two instruments are not synchronized. And so we'd have to derotate the IQ vector, and that requires some additional math post-processing after the fact. So there's another solution to that, and we can actually just do an analog demod on the signal. So I'm going to switch this back to external for now. Let's go ahead and open up an analog demod channel and see what we can do with that trace. As before, we're going to change our acquisition time to 5 milliseconds. Change the trigger to external 1. We'll reduce the demod bandwidth to 1 megahertz. Same thing as the resolution bandwidth and the IQ analysis bandwidth from before. And we'll change the displays. So we'll add in a RF time domain trace. We'll add in an AM time domain trace, which is pretty similar to the RF time domain. It's just an exponential ramp rather than a linear ramp. And finally, let's add in a PM time domain. This is going to show us the phase deviation versus drive level. So now we have basically the same information as before, but it's already done the math for us. It's worried about that derotation. We should even be able to turn off that frequency reference. And it's still able to handle that signal just fine. And let's go ahead and finish up the scales on these so we have a useful result. So let's change the vertical scale. Right, and there we have it. This is the amplitude and phase linearity of this amplifier using the analog demodulation application.